In this video, we will go over chemical concentrations, molarity, formality, normality, molality, weight percent, weight to volume percent, ppm, ppb, p functions, stoichiometric calculations, and preparing solutions. The textbook is David Harvey's, Analytical Chemistry 2.1. The concentration is a general measurement unit that reports the amount of solid present in a known amount of solution. The overall generic formula for the concentration is the amount of solid divided by amount of solution. And the common units for reporting concentration, we got molarity, which is moles of solid per liters of solution, with the symbol of capital M. Formality has the same unit, moles of solid to liters of solution. The symbol is F, capital F. We got normality, equivalence, solid to liters solution, and the symbol is N. The molality is moles of the solid divided by kilograms of solvent. The unit, the symbol for molality is lowercase m. And we got weight percent, and also weight percent is grams of solid per 100 grams of solution. The symbol is percent, weight by overweight, weight by weight. The alternative expression for weight percent is mass of solid divided mass of solution times 100 10 to the second, which is 100. Volume percent, if we're dealing with liquids, for example, most of the time we use the volumes, so alcohol and water. So we can have 80 milliliters of water, 20 milliliters of alcohol. So that we will use volume instead of mass. But if we want, we can use mass as well. So the the expression for volume percent would be volume of the solute divided by the volume of the solution times 100. Weight to volume, I mean, we can have also the weight of the solute and volume of the solution. So that will be the volume of solute divided by volume of solution times 100. The parts per million, the definition is grams of solid divided by million grams of solution. So if we have a million solution, we can split it to million even pieces, even amounts. So each one will be parts per million. And the alternative expression for ppm would be mass of the solid divided mass of the solution times million. And finally, we got parts per billion, which is mass of the solute divided by the mass of the solution times billion, 10 to the 9th. So the molarity here is and formality, they both, as we saw in the table, they have the same formula, the same the moles of solid per liters of solution. There's a slight difference between them. So the molarity is the concentration of a particular chemical species. Formality is a substance's total concentration without regard to its specific chemical form. For example, if we have a chemical that doesn't break into its parts or ions, then the molarity and formality will be the same, like glucose or alcohol and so on. But if we're dealing with the ions, for example, calcium chloride, as soon as we dissolve it in water, it breaks down into calcium ions and chloride ions. So as we see it here, it's one mole calcium chloride breaks down to 1 mole calcium ions and 2 moles of chloride ions. So in that case, this is where we see the difference. So the calcium chloride in this solution here, the calcium chloride concentration would be 0 because there is no undissociated calcium chloride in the solution. All of it breaks down to its ions. So that's why the formality of of this solution would be 0.1 molar if 1 mole of calcium chloride is dissolved in solution in water. But most of the time we call it 0.1 molar calcium chloride. But we should we understand that that it is actually the solution actually consists of calcium ions and chloride ions, that we don't have any undissociated calcium chloride in the solution. So that's the difference between molarity and formality. In most of the time, many times we see the square brackets and the ions or chemical species are shown in square brackets. That means the molar concentration. So if we have calcium ion, for example, between square brackets, it means the molarity of calcium ions. The normality is no longer in use, but it is basically defined as the molarity times n. So this n is kind of the number of for acids, for example, the number of species that interact with other species. For HCl, hydrochloric acid, it is 1 because HCl gives off 1 hydrogen to react with bases, for example. Sulfuric acid, for sulfuric acid, it will be 2 because it has 2 hydrogens. For redox reactions, depending on how many electrons have been traded or are being traded in a chemical reaction. So for HCl, for example, the normality and molarity would be the same. For sulfuric acid, the normality would be double of the molar concentration. The molality is the moles of the solid divided by the kilogram of the solvent, and that is so it is independent of the temperature, and that's why it is used in thermodynamic calculations. The because molar concentration changes with the temperature, because the molar concentration is the moles of the solid divided by the volume of the solution. So volume changes, volume of water or any other solvent or solution changes. And thus the molar concentration. So that's why in thermodynamic calculations we use molality frequently. The other we got weight, volume. We already went over those, and what that means. Let's say we got a solution of 1.5% ammonium nitrate. So 1.5%, that's the mass per volume, means out of 100 ml of solution, 1.5 gram is ammonium nitrate. So the parts per million, ppm and ppb, these are whenever we have really dilute solutions or very low concentration. We prefer to use ppm or ppb instead of molarity or percentages. So what ppm means, ppm again is mass of solid divided by mass of solution times million. So for example, if we have a sample of steel that is 450 ppm in manganese, contains 450 microgram of manganese for every gram of steel. So, and of course, in this assumption, we have assumption that the density of the solution, the aqueous solution, is equal to the density of water. So it's so dilute so that the otherwise this the assumption would not be accurate. So the ppm is microgram of solid per gram of solution, or milligram of solid per liter of solution, or we can have microgram of solid per milliliter of solution. The ppb, on the other hand, is nanogram of solid per gram of solution, or microgram of solid per liter, or nanogram of solid per milliliter of solution. For gases, a part per million usually is expressed as a volume ratio. For example, a helium concentration of 6.3 ppm means that 1 liter of air contains 6.3 microliter of helium. That is for gases. We most of the time we have to convert between concentration units, again, so here we will see a few examples. Again, for us to be able to use microliters, ppm or ppb, we have to make sure the concentration is really, the concentration of solution is 1 gram per milliliter. So in example 2.2 here, a concentrated solution of ammonia is 28% weight per weight ammonia, and has a density of 0.899 grams per milliliter. What is the molar concentration of ammonia in this solution? So first, when we look at the we will first look at what is given in this question. So there are two numbers here. The 28% weight by weight means 100 grams of solution. This solution contains 28 grams of ammonia. The other is the density of the solution. And also, whenever we deal with molar concentrations, we usually need the molar mass of the chemical, in this case the ammonia. So using those, the goal is we start with the 28 grams of ammonia per 100 grams of solution, and we end up with mole of ammonia per liter of solution, because molar concentration means the mole of the solid, which is in this case the ammonia, divided by the liter of the solution. So we start with the percentage of ammonia here, 28 grams ammonia per 100 grams of solution. We could also start with the density. It doesn't matter, because A times B or B times A are equal. So here, in this first step, we are basically converting this solution, gram solution here, this gram solution. So we're trying to basically get rid of the units and end up with mole ammonia here, as we see it here, per liter of solution. So that is molarity. And then we just once we handle the units, we handle the units in the first, the second here, the first step. We convert the gram solution per so the solutions are ammonia. A gram solution, gram solutions is kind of, they cancel out, and then we got ammonia here. The grams ammonia are being converted to moles of ammonia, and then we in the final step here we convert the volume in milliliter to liters, so that, because in molarity the denominator is the liter of the solution, and the rest is just the math. 28.0 times 0.899 times 1 times 1000, and then divide by 100, and whatever number we get, we divide it by 17.03, and we come up with 14.8 molar. So that is the the molarity of the solution that we have in this question here. This second question deals with a conversion from ppm to molarity. Again, here we have to know that what ppm means. If we remember, it is a milligram of solid per liter of solution. So instead of ppm, we use milligram chloride per liter of solution. And then, so the goal here would be, we start with milligram per liter solution. We end up with moles of chloride per liter of solution. So we don't have to deal with the liter, which is already there. We just need to convert the milligram of chloride, for example, is 1 gram chloride. So that will cancel out. And then, of course, we need to convert gram chloride to mole chloride. So to do that, we have to use the molar mass of chloride. It is not given in the question, but we have to have it. We can find it from periodic table also. And so once we cancel out the units, we have mole chloride per liter of solution, and then we just do the math. 2.550 10 to the second times 1 times 1, so it's the same, divide by 1,000, and then divide by 35.453, and so we come up with 7.05 10 to negative third. So we have to have three significant figures here, because we got three significant figures here. So again, this is the conversion from ppm to molarity. This is another question. Again, here we do the opposite from molarity to microgram per milliliter, which is ppb, microgram per ppm, sorry. So we can do that. So we know the molarity is mole solid divided by the liter of solution, and here we got we go from mole solid per liter of solution to microgram of solid per milliliter of solution. And for sodium chloride, we start with the molarity. So 0.50 molar means 0.50 mole sodium chloride per liter of solution. Again, so our goal is to go from mole sodium chloride to per liter to microgram solid, in this case sodium chloride, per milliliter of solution. So we will have to convert mole of sodium chloride to microgram sodium chloride, and also the liter of solution to milliliter of solution. And so that's why we have to use in the first here, our goal is to convert mole sodium chloride to gram sodium chloride, and in second we convert gram sodium chloride to microgram sodium chloride. So we can put sodium chloride, and then finally we convert the liter here, this liter to milliliter. So by doing that, we are done basically, and then the rest is basically so we got microgram of solid table salt per milliliter of solution, and then we just do the math here. 0.5 times 58.44 times million 10 to 6, and then divided by 1,000 and so on. So you come up with 2.9 10 to 4th microgram per milliliter sodium chloride. And if we do it for sodium chloride, we do the same thing. We will start with the molarity, which is 0.25 moles of solid per liter of solution. We use molar mass of sodium chloride to convert moles to grams, and then we use the relationship between grams and microgram, because 1 gram is 10 to 6 microgram, and then the liters to milliliters. So what is left is microgram of solid per milliliter of solution, and that is what we're looking for. So once you do the math Here you come up with 4.010 to 4th microgram per milliliter strontium chloride. And as you see, the second one is greater than the first one, strontium, if we show it in microgram per milliliter. But in molarity, the first sodium chloride is greater, is higher concentration, molar concentration than strontium. It's almost double. It's double. The other concept is the P functions. So many times when we're dealing with concentrations, the concentration may change by many orders of magnitude. And so instead of using molarities or other concentration, we prefer to use P functions. For example, in this graph here, we got hydrogen ions. We got hydrogen ions that start with 0.1 molar. Here we got hydrogen ion concentration 0.1 molar. And it changes as a factor of sodium hydroxide volume. So as it reacts with hydroxide ion, it is converted to water. So the concentration of hydrogen ion goes down, and around here it goes down to 4.3, 10 to negative 13. It's really low concentration. So in these cases, we prefer to use a P function instead of molar concentration. So what is P function? P function is a pH. pH is basically the negative log of hydrogen concentration. If we use any other ion, calcium, for example, P calcium concentration. So that will be negative log of calcium ion concentration. So that is how we convert a concentration to pH or P, whatever the ion we're dealing with. Here we got an example. What is PNA for a solution of 1.76 times 10 to negative third molar sodium phosphate? Again, sodium phosphate is a soluble salt, and when it breaks down to 3 moles of sodium and 1 mole of phosphate. And so if the initial concentration of sodium phosphate is 1.76, 10 to negative 3 molar, the molar concentration of sodium would be triple of that, because each mole of sodium phosphate breaks down or generates 3 moles of sodium, so the molar concentration will be 3 times. The phosphate ion concentration will be the same. We don't worry about phosphate at this point because we're looking for PNA, and so that's why first we have to find the molar concentration of sodium ions, and that is 3 times 1.6, 3 times, and here we can set it up, and each mole has 3 moles of sodium, so you come up with 5.28 10 to negative third molar, and the rest is just take the negative log of that concentration, so negative log of 5.28 10 to negative third, and if using your calculator you come up with 2.277. So since we need to watch for the significant figures here, the the significant figure is 3 after the decimal point, because that 2 is related to the log. So basically 2.277 we got 3 significant figures. Okay, what is the hydrogen ion concentration in a solution that has a pH of 5.16? That is also related to P function. This is a reverse of that. So, again, here the pH is given. We're looking for hydrogen concentration. In previous questions, the concentration was given. we're looking for pH or PNA. So we have to, we can rearrange it. If log X, the concentration equals to A, then X would be 10 to the power of A. And here pH equals to negative log of hydrogen ion concentration, and that is equal to 5.16. So then you can multiply both sides by negative, and so you come up with basically move this this negative sign here to the other side, and so you come up with this formula. And again, compare with this one here. So you can rearrange, leave the hydrogen ion concentration alone. It will be 10 to negative pH, which is given in the question, 5.16. And if you solve it using your calculator, you come up with 6.9, 10 to negative 6 molar. So when the pH is 5.16, the hydrogen concentration is 6.9, 10 to negative 6 molar. What are the values, another question, of PNA and PSO for if we dissolve 1.5 grams of sodium sulfate in a total solution volume of 500 milliliter? Again, the target here is to find the concentration of sodium ions and sulfate ions using that mass of sodium sulfate. So again, we start with 1.5 grams dissolved in 500 mils. So notice that we convert the milliliters divided by 1,000. You come up with 0.500 liters. This is where we use it. So it's grams per liter, and the goal is to convert grams of sodium sulfate and to moles and so on. And then we relate it to sodium ions, because each mole of sodium sulfate generates 2 moles of sodium ions. And you cancel out, you come up with mole sodium divided by liter of solution, and that is 4.23, 10 to negative 2 molar sodium. And here you notice that we have a 3 in red. The reason is we must have 2 sig figs here. Because the operation is not over yet, we keep an additional sig fig. So actually the uncertainty here in the second and the 10th place there, but we keep another addition until we finalize the solution. We do the same thing for sulfate. Again, the concentration of sulfate would be equal to the concentration of sodium sulfate, because there is 1 sulfate ion per 1 mole of sodium sulfate, and you come up with 2.11, 10 to negative 2 molar. And now it is time, once we find the molarity of those species, we can take the negative log of those. For sodium, it is 1.37. For sulfate, it is 1.68. So another question here, what is the pH of a solution for which the concentration of hydrogen is 6.92, 10 to negative 6 molar? And what is the hydrogen ion concentration in a solution whose pH is 8.923? So we solve similar questions again here. It is a P function. So pH, as long as we have the hydrogen concentration here, we take negative log of that, and we come up with 5.160. So the other one, we take this is anti-log. So hydrogen concentration will be 10 to negative pH, which is 8.9. So we do the math, we come up with 1.19, 10 to negative 9 molar. Now, then we can talk about the stoichiometric calculations, a balanced reaction basically. In stoichiometric calculations, we can find an unknown based on the known species in a reaction. So, but first we have to make sure the chemical reaction is balanced. So this is one example. It is iron 3 ions react with oxalic acid. It's basically oxidizes oxalic acid, and so we can find the amount of oxalic acid using if we know the concentration and the volume of iron 3 solution. For example, iron 3 chloride, for example, we can find that, and 1 mole oxalic acid reacts with 2 moles of iron. So that's what we see here. Is the stoichiometric equivalency, basically. So and if we know the moles of iron, which can be calculated if we know the volume of the solution, iron solution, and the concentration of the iron solution, we can easily find the moles of iron, meaning because we know molarity equals to moles over volume. So if you arrange it for moles, it will be molarity times volume. So for any solution, if we know the molarity and the volume, of course, the volume has to be in liters because the molarity is moles per liter. So you have to do the concentration conversion, of course, to find it. So let's see an example here. The amount of oxalic acid in a sample of rhubarb was determined by reacting with iron 3 ions. After extracting a 10.62 grams of rhubarb with a solvent, oxidation of the oxalic acid requires 36.44 milliliter of 0.0130 molar iron solution. What is the weight percent of oxalic acid in the sample of rhubarb? So this question is clear, right? We have a plant, but just 10.62, and in this plant we have oxalic acid. And so after we extract the oxalic acid from this sample, 10.62 gram of the sample, we consumed 36.44 mils of 0.013 molar iron. So how much? So we're looking for what is the weight percent of oxalic acid in the sample of rhubarb plant, basically. So we begin by calculating the moles of iron because again here we have the relationship between iron and oxalic acid. Here is 1 to 2, and so because we got the molarity of iron, so that's 0.03, that's moles of iron 3 ions per liter of solution, and times the volume here. Again, remember here we have to convert it to liters by dividing, so you just divided by 1,000, and now you got so liters will cancel out, and so we got moles of iron. So we got 4.737 times 10 to negative 4 moles of iron. Now, according to reaction here, we got 2 moles of iron react with 1 mole of oxalic acid. So then that means we have to have half of that, because if we got this many moles of iron in hand that reacted with oxalic acid, so that means 1 mole or half of 4.7 because 2 mole again. So we start with that. 2 moles of iron react with 1 mole oxalic acid from the balance equation, and you come up with 2.368 10 to negative 4, which is half of that, 50%, half of that. So in next we convert the moles of oxalic acid to grams of oxalic acid here, because we know the molar mass. We can get it. We can calculate it. We got 2 hydrogens, 2 carbons, 4 oxygens. So you come up with 90.03 grams is 1 mole. So mole will cancel out, and you come up with grams. So 2.132 10 to negative 2 grams of oxalic acid, and so Again, this much oxalic acid is obtained from what 10.62 grams of the rhubarb, and so to find the percentage, weight percent of oxalic acid, so we divide this mass here by the mass of the sample, which is 10.62 and times 100, and that will give you 0.201% weight per weight oxalic acid. So that's a good example of stoichiometric calculations. Again, one thing we need to keep in mind that we have to have the balanced reaction. If the reaction is not balanced, there is no way we can come up with the correct answer. The second, if the molarity and the volume of a species, one of those species here, we got two major ones. The iron 3 oxidizes the oxalic acid because it is reduced here, so it is oxidizing agent. Iron 3 is the oxidizing agent here. And so if we know if it is solution, if we have the volume and the concentration, we can find the moles, and then we can relate it to the other species here. In this case, the oxalic acid. What else? We got another example here. You can dissolve a precipitate of silver bromide. It's not soluble actually. It's not. Well, sparingly, or it's not soluble in water. But if you add, if you dissolve it in sodium thiosulfate solution, you can dissolve a silver bromide. So how many milliliter of 0.0138 molar sodium thiosulfate do you need to dissolve 0.25 grams of silver bromide? Again, here we got the balance equation. This is another way of writing it, but this is it's better. You can see silver bromide, and it is 1:2 ratio. So we know the mass of here. We don't have we have the concentration of sodium thiosulfate, but we don't have the volume, so we cannot convert it to moles. But because we got mass of the silver bromide, and we know we can calculate the molar mass of silver bromide, we can convert that into gram will cancel out to moles. So 0.250 gram of silver bromide equals to 1.331 10 to the 3rd moles of silver bromide, and then you can convert that to find. You can use that to find the number of moles of thiosulfate, sodium thiosulfate that is enough to react with that. So again, it is 1:2 ratio. So if we have this one, you have to double, because 1 mole silver bromide react with 2 moles of sodium. So if you have 1.331 10 to the -3 mole of silver bromide, that means you have double of that of sodium thiosulfate. And from there, we're looking for how many milliliters of solution. So we got the moles of thiosulfate, we got the volume of the concentration of, so you can find maybe basically once you get the you can find this, you have 2.662 10 to the moles of sodium, and you got the concentration means the 0.0138 moles of thiosulfate is present in 1 liter of solution. So that's 1 liter, and the moles will cancel out here. So you come up basically, and then here, because it's asking for milliliter, we have to the liter here to milliliters, and this is what we do basically. So they will cancel out. So that means the liters will cancel out. So we got milliliter left basically. So you multiply these numbers, that divide by this number, you come up with 193 milliliter of the sodium thiosulfate solution. Now here, you can do that if you don't feel comfortable with this here. So we got moles. Here we got concentration. So we can find volume. Remember, molarity equals to moles over volume, and so volume, if you rearrange that, volume would be N over concentration. So 2.66 to 10 to negative 3 moles. The concentration is 0.0138 moles per liter, and so on and so forth. So basically you do the same thing here. You come up with 193 milliliters. So to react with 0.250 grams of iron 2, what mass of 3% hydrogen peroxide solution is required to provide a 50% excess of reagent, in this case the hydrogen peroxide, for the following reaction. So basically what you have here, you got iron 2, that's ferrous iron, reacts with hydrogen peroxide, and hydrogen peroxide, you know, it is oxidizing agent, so it oxidizes iron 2 to iron 3, so here we have 0.250 grams of that of iron. So how much hydrogen peroxide is required for this reaction? And also, again, it's not only how much it is required, we have to have 50% excess of that. So first, let's convert 0.25 grams of iron to moles of iron. So, and that's how you use it, right? Grams and molar mass. So grams iron's gone, and you come up with 4.477 10 to negative third moles of iron. And then, so in the balance equation, you know, 2 moles of balance reaction requires 1 mole hydrogen peroxide for every 2 mole of iron 2, as we see there. And so that gives you basically, so you can use that to find the moles of hydrogen peroxide that is required. That's 2.239 10 to negative third, which is half of this, half of that. So, and then you can see the balance equation here is 2 to 1. So if you don't have any number, any coefficient in front of a reagent or chemical, that means 1. It doesn't mean 0. So a 50% excess of hydrogen peroxide means that we will need 1.5 times of 2.239 10 to negative third moles, right? So that's 50% excess. So that's so we have to multiply it by 1.5. So you come up with 3.359 10 to negative 3 mole of hydrogen peroxide. So that is if we didn't need that 50% access, then this would have been our answer. But convert, so here we convert the moles of hydrogen peroxide to grams of hydrogen peroxide. So, and that is, we just multiply it by the molar mass of the hydrogen peroxide, which is 34.01 gram. And so moles hydrogen peroxide has gone, so you come up with 0.1142 grams hydrogen peroxide. Again, what is the source of this hydrogen peroxide? 0.1142 grams. It's the hydrogen peroxide solution, which is 3%, right? 3% means the 100 gram of solution, only 3 gram is hydrogen peroxide. So to get this pure hydrogen, this much pure hydrogen peroxide, how much solution do we need? That is the question here, because hydrogen peroxide is available as a 3% weight percent solution. So the required mass of hydrogen peroxide solution is, so because we know that we need this much here, this much hydrogen peroxide, and also we know that 3 grams of hydrogen peroxide is present in 100 gram of solution. So you come up with basically 3.81 gram hydrogen peroxide solution. So if you get that much, if you measure that much hydrogen peroxide solution, you would have this much here, this much hydrogen peroxide that will react with iron. Of course, this 50% excess. So again, here we got another example in stoichiometric calculations. This time is the sulfurum is a chemical here with the chemical formula of C10H20N2S4. There are 4 sulfur atoms per mole, and per molecule of the sulfurum here. It is an active ingredient of the drug antabuse, and it first is required to convert the sulfur to sulfur dioxide, and then by combustion, of course, and then to oxidize the sulfur dioxide to sulfuric acid. And once we get the sulfuric acid, and then we react with this titration with sodium hydroxide. So from there you can, it's basically for all the sulfur that we got in sulfuric acid, it comes from the sulfuram here. And the reaction between sulfuric acid and sodium hydroxide here, it is balanced reaction. So 1 mole sulfuric acid requires 2 moles of sodium hydroxide. So if you know the volume and the concentration of sodium hydroxide, you can find the moles, and from there you can relate it to sulfuric acid and so on. So you can find the amount of the analyte, the sulfurum here. So let's work on one example here, an analysis for the sulfuram in antabuse drug is carried out by oxidizing the sulfur to sulfuric acid and titrating the sulfuric acid with sodium hydroxide. If a 0.4613 gram sample of antabuse requires 34.85 mils of 0.02500 molar sodium hydroxide. You see we got both the molarity and the volume of sodium hydroxide. Titrate the sulfuric acid. What is the percent weight by weight the sulfurum in the sample? So again here, as we solved one, because we got the volume and the concentration of sodium hydroxide, we can find the moles of sodium hydroxide. So, and that is here. So this is the concentration. So molality is mole sodium hydroxide per liter sodium hydroxide. So the volume here, we converted that to liters, of course, because here we got liters, it has to cancel out. So divided by 1,000, you come up with 0.03485 liters, and you come up with this many moles that is required to neutralize sulfuric acid, which was generated from the sulfuram, the compound. And then we use the titration reaction stoichiometry to calculate the corresponding moles of sulfuric acid. Again, if we got 8.1725 10 to negative 4 moles of sodium hydroxide, and we know that 2 moles of sodium hydroxide are required for 1 mole of sulfuric acid, so you come up with 4.35, which is half of that according to reaction, half of that. So if we got 2 moles of sodium hydroxide, we need half of that 1. So here we got 8.7125 10 to negative 4 moles of sodium hydroxide. So we need half of that, which is 4.3562 10 to negative 4 moles of sulfuric acid. So here again, because we know all the sulfur is coming from the sulfuram, then we can relate it to, we can find the amount that. So this is kind of conservation of mass. So all the sulfur comes from this compound here. So the sulfuric acid, remember there? So we can convert it to relate it to moles. So again, so we got 4.3562 10 to negative 4 moles of sulfuric acid. We know 1 mole sulfuric acid has 1 mole sulfur, and also 4 mole sulfur, they come from 1 mole disulfiram. And so basically, once you cancel out, you come up with 1.089 10 to negative 4 moles of the disulfiram compound. So that's the, see, we find the moles of the sulfur from moles of sulfuric acid because all the sulfur in the sulfuric acid comes from the sulfuram compound. So that many moles of the sulfuram, we know 1 mole, we just converted to grams of the sulfuram, and so that many moles equals to that many grams of 0.03229 grams of the sulfuram. And so to convert that, so remember the initial tablet contains sample of antabuse contains 0.461 gram of sample. So we divide the mass of the sulfuram divided by the mass of the drug, the tablet, times 100. So you come up with 7.000%. So that's sig figs. We have to have 4 sig figs there, and percent of the sulfuram in the tablet. So 7% of the tablet is the sulfuram. The rest is just fill-in material and other things. So that's the. So let's talk about the preparing solutions. Again, in analytical chemistry, we have to prepare a lot of solutions to titrate and so on. So whatever the problems that we've worked so far, all of them almost were solutions. So you have to deal with the solutions. You have to make the solutions and so on. So, for example, if you're finding, let's go back here. So in this example, you have to prepare this sodium hydroxide solution really accurately so that you can find the amount of the sulfuram accurately. So, so making solution is really crucial. For example, we got a variety of glassware to measure the volumes. To make solutions, you have to measure the amount of solvent and so on and so forth. So pipettes and volumetric flasks are used when we need to know a solution's exact concentration. So if we want to be really accurate and precise, we have to use pipette and volumetric flask. Sometimes we don't have to be accurate. In that case, we can use graduate cylinder, beakers, or reagent bottles. So whenever we need approximate, sometimes it says approximately 0.1 molar sodium hydroxide. That means we don't have to be that accurate. If we want to make 0.0100, that in that case we have to be really accurate. So the stock solution, in most of the case, we make a stock solution with higher concentration of chemical, and then from that we can make dilutions to make desired different solution concentrate with different concentrations. So instead of weighing the chemical and making new solution, that is one way of making dilution. So for that we need to prepare stock solutions. Here we're asked to describe how to prepare the following 3 solutions. A 500 milliliter of approximately 0.20 molar sodium hydroxide using solid sodium hydroxide. Sodium hydroxide is solid, of course, so You see, you notice that there's approximately 0.2 molar. The second one is 1 liter of 150.0 parts per million copper to solution using copper metal. And the third one is 2 liter of 4% volume per volume acetic acid using concentrated glacial acetic acid, which is 99.8% with acetic acid. So the first one is because the desired concentration is known to two significant figures. The first one is 0.20, so that we got two significant figures there. We do not need to measure precisely the mass of sodium hydroxide or the volume of the solution. So the desired mass of sodium hydroxide, we can do the calculation 0.02 moles of sodium hydroxide, that's the molarity per liter of solution. And then we know that 1 mole of sodium hydroxide is 40 grams, and that the final volume, so here we converted the moles to grams, and then the volume here we need 500 milliliters. So to convert this, to get rid of that, we basically cancel out the moles, the liters, and you come up with 4.0 grams of sodium hydroxide. So basically, to prepare the solution, we place 4 grams of sodium hydroxide. The weight to the nearest tenth of a gram. So it doesn't have to be really precise. It doesn't have to be really, 100th or 1000th place. It is just 10th place, nearest 10th place in a bottle or beaker, and then add approximately 500 ml of water. So that is enough to make this approximate solution. The second one, if you look at here, the desired concentration of copper is given to 4 significant figures. So this is 4 significant figures. That means we must measure precisely the mass of copper metal, and the final solution volume has to be precise as well. That's why first we need to do the calculation because we want to make 150 milligram copper per liter, which is ppm, right, parts per million, and we want to make a liter of solution, that cancel out, and also milligram, we convert milligram copper to grams, and so you come up with 0.1500 gram copper. To prepare the solution, measure out exactly. You see, it's not approximate, it's exactly, because it has to be. It is 4 stick figs, 0.15 grams of copper into a small beaker, and dissolve it using a small portion of concentrated nitric acid to ensure a complete transfer of copper 2 ions from the beaker to the volumetric flask. This is a volumetric flask, what we call a quantitative transfer. Rinse the beaker several times with small portions of water, adding each rinse to the volumetric flask. So make sure you don't exceed the 1 liter mark. So you dissolve it in a beaker, right? And then you rinse it several times to the volumetric flask. But you gotta watch for the volume. Make sure it doesn't exceed at least around here. And then you can add water. Then we can add water to this mark. The marks, if this is mark, make sure the bottom of meniscus is on the mark. So that's the how we measure, how we prepare this solution. The third solution is 2 liter. We want to make 2 liter 4% acetic acid, volume per volume acetic acid solution. Again, the concentration of this solution is only approximate, so it is not necessary to measure exactly the volumes, nor is it necessary to account for the fact that glacial acetic acid is slightly less than 100%. It is 99.8%. So that's why 4 milliliter, 4% means 4 milliliter acetic acid in 100 ml of solution. solution. So we want to make 2,000 milliliter. So milliliter would cancel out. And so you come up with 80. If you do the math, those two zeros would cancel out those two zeros. 20 times 4, so you got 80 milliliter acetic acid, glacial acetic acid, and you can use a graduate cylinder to measure this much, 80 mils of acetic acid, and then you add. You transfer to a container, a beaker, 2-liter beaker, or whatever glassware you got, and add water to the mark. Or 80 plus, you can add how much? 1920 solvent, which is water in most cases. So provide instructions for preparing 500 milliliter of 0.1 to 50 molar potassium bromate. Again, here first we need to find out how many grams of potassium bromate we need, and to do that we have to start with the liters, which is 0.5. Again, this has been converted to liters, and that's the volume times this is concentration. The second portion is concentration, so liter will cancel out, and you come and then you multiply by the molar mass, and you come up with 10.44 grams of potassium bromate. Again, if you're looking for mass of a solution, if you know the volume, the concentration, the molar mass, so mass, lowercase mass, equals to molarity times volume times molecular weight, or molar mass. You see, that's what we have. We got volume, we got concentration, we got molecular weight. If you multiply those three, you come up with the mass that is required to make that solution. That's one step, straightforward procedure to find the mass. Of course, you need to convert the volume from milliliter to liters. Because the concentration has 4 sigma figures, we must prepare the solution using volumetric flasks. So volumetric flasks are really precise, accurate. So place 10.44. We need to weigh that exactly that much, 10.44 grams of potassium bromate in a volumetric flask. So you weigh that much, you transfer it here. Now it is here. That's 10.44 grams. And then you add water, about this much water. Dissolve it completely, just swirl it really well, mix it really well until it is completely, once it is completely dissolved, add a little bit more water, so just make sure all the crystals are dissolved, and then you can add water to the mark. So that's how you make this solution. Okay, preparing solutions by dilution. Again, as we mentioned earlier, that we can make a stock solution with higher concentration, and then we can prepare dilute solutions out of that. So now the thing is, you see, now here, since the total amount of solid is the same before and after dilution, we can write this one. What does that mean? Because let's say we got this beaker, same beaker, and initially we got 2 moles. So each circle represents 1 mole, and let's say this is 1 liter. So the concentration of this one is 2 moles per 1 liter, so that is 2 molar, right? So let's say we to the same solution we added another liter of solution. Now we got 2 liters, still 2 moles, and so the concentration will be 2 moles divided by 2 liters is 1 molar. You see, we doubled the volume, keeping the moles constant. So the concentration went down from 2 molar to 1 molar. You see, in both cases, the N initial equals to N dilute solution. So, and remember the molarity is what? Molarity is N over volume, so N equals to molarity times volume. So that's why here instead of molarity we use C, or you can use a capital M or C, doesn't matter. So as long as we know that C0 is the stock solutions concentration, the initial concentration, so V is the initial volume, CV is the dilute solutions concentration, and VD is dilute volume concentration, dilute solutions volume. So so basically that's what we mean here, because initial volume and initial moles and final moles are equal. That means we can come up with this equation here. Initial concentration times initial volume equals to final concentration times final volume. And so let's erase here. All right, so again, this equation is used for almost all the concentrations, with the exception of the molality. So we cannot use this formula to find the molality to make the dilutions. Just keep that in mind. So here a question: a laboratory procedure calls for 250 mils of an approximately 0.10 molar solution of ammonia. Describe how you would prepare this solution using a stock solution of concentrated ammonia, which is 14.8 molar. Now, what we have here, we got the dilute volume, so the dilute solution volume, 250 milliliters. We have the concentration of dilute that we want to make, 0.10 molar. We also have the stock solutions concentration, which is 14.8. Now in molarities, when we make solutions, we mentioned that we have to convert the volume to milliliters. I mean milliliter to liters. Now in dilutions, we don't have to do that. We can use milliliters. So to solve this one here, first we need to we have the 14.8 more or less stock solution concentration here, and here this is what we're looking for, question mark, yeah, here, and equals to the dilute solutions concentration, 0.01 molar, and the volume, as you see here, we don't have to convert it to milliliters. And so if you do the math here, you come up with rearrange it for V sub 0, that's dilute solutions volume. And 0.10 molar times 250 milliliters divided by initial concentration, stock solution concentration, 14.8 molar, and that's 1.7 milliliters. So so we solve it for 1.7, since we are making a solution that is approximately 0.1 mol, 110 molar ammonia. We can use a graduate cylinder to measure the 1.7 milliliter of a concentrated ammonia, transfer the ammonia to a beaker, and add sufficient water to give a total volume of approximately 250 milliliters. So again, I mean, we can use 250 milliliter volumetric flask, but we don't have to. If this kind of solution is asked, we don't have to be precise. But if you want to do this, if you want to use this for, let's say, determination of an acid, let's say acetic acid in vinegar, then you have to be careful when you make this solution. It has to be really 0.100 whatever concentration, so it has to be precise. So the molarity of concentrated HCl is approximately 12.1 molar. How many milliliters of this solution should be diluted to 500 milliliter to make a 0.1 molar HCl? Now again, this is a dilution, so we got the stock solution concentration 12.1 molar, and we have the final volume. We want to make 500 milliliter solution. That's the volume of the final dilute solution, and we also have the concentration of the dilute solution. So everything is here, and using the dilution equation again, instead of C, we can use M. Sometimes we use M1V1 equals to M2 V2. M1 stands for initial concentration, V1 is initial volume, and so on and so forth. Again, the symbols might be different, but the idea is the same. So we rearrange for the initial volume, so that will be the dilute concentration times dilute volume. So divided by the initial concentration, so that's 0.1 molar times 500 milliliter divided by 12.1 molar, and you come up with 4.18 molar. Now, if you somehow don't remember the formula, you can use the logical way, or we know that as I showed earlier, when the volume goes up, keeping the number of moles constant, when you increase the volume, you decrease the concentration. So the concentration and the volume of the solution are inversely related. So when one goes up, the other goes down, and so on. So here we start with 12.1 molar, and we end up with 0.100 molar HCl. So that's how many times. That's, you divide 12.1 by 0.100. That is 121 times dilution. 121 times dilution. So that means, so what number is 120 the 20th part of 500? Because remember 500, so we start with a number and we add up to 500 milliliters, so it should be 121 times. So basically, if you divide 500 by 121, you come up with 4.13 milliliters. That means if you measure 4.13 milliliter and increase the volume 121 times, that is 500. So you can use this way of solving the problem. I think this is last question here. A solution is made by adding 38.6 milliliter of concentrated nitric acid, and that is 70.4 weight percent, and the density of that solution is 1.42 grams per milliliter, to some water in a volumetric flask, and then adding water to the mark to make exactly 500 milliliter of solution. Calculate the concentration of this solution in molarity. So again, first we need to find the initial concentration of nitric acid using its weight percent and density. So that's 38.6 milliliter of concentrated nitric acid. The solution, we know 1 milliliter solution is 1.42 grams of solution. That's from the density, and that we come up with 54.8 grams of solution. Again, it is not the grams of nitric acid yet. So we then find the amount of nitric acid in this solution, because only 70.4% of this solution is nitric acid. Again, not all of that 54.8% is nitric acid, only 70.4%. So we need to find that so we can multiply that by 0.704, which is here, to find the 70.4% of that, which is 30. We come up with 38.6 grams nitric acid. And then we find the moles of nitric acid using its molar mass. So remember this much, was the mass of nitric acid. So if we divide it by molar mass of nitric acid, which is 63.01 gram, we come up with 0.61 moles of nitric acid. Now this is just an extra here because we're going to use all of it in our solution. We don't have to go back. Here, if you wanted to calculate the molar concentration of nitric initial constant, because it is not given there, it's only the percentage and the density is given. So once we find the moles of nitric acid, we can divide it by initial volume to find the initial concentration, which is 15.9 molar. But in this question, we don't need to do that. That is just side thing. So 0.613 moles of nitric acid were diluted in a final volume of 500 milliliters or 500 liters. Thus, the final concentration of nitric acid is, we just divide that by the final volume, that's moles of nitric acid, and you come up to 1.23 molar nitric acid. Okay, you can pause the video. You can work on this problem again. It's kind of lengthy, but it looks complicated. But once you watch it once or twice, you will get it. An analyst wishes to add 256 milligram of chloride to a reaction mixture. How many milliliter of 0.217 molar barium chloride is this? So again, the source of chloride, we need 256 milligram of chloride, and that chloride comes from barium chloride with a concentration of 0.217. Again, we convert the milligram chloride to gram and then to mole of chloride. We know that 2 mole of chloride is present in 1 mole barium chloride, and then 1 mole, the concentration 0.217 mole barium chloride is in 1 liter of solution, and then we can convert it to milliliters, so that will be 16.6 milliliter of barium chloride solution. So you see it is it's how many steps? 1, 2, 3, 4, 5, 6, whatever steps. You can continually put them together. It's just conversion from one. Let's go back again. So you start with 256 milligram chloride. First you convert milligram to grams, right? Grams. And then the second step is we convert grams of chloride to moles. So grams will cancel out. So now we got moles, and the moles we know now you can relate it to moles in barium. We know 2 moles of chloride are present in 1 mole barium chloride, so mole chloride are gone because we want to start with milligram chloride, end up with milliliter of barium chloride, and that's how the steps we take. And then finally we got 60.6 milliliter of barium chloride solution, so that will give us 256 milligram of chloride. Another question here, a 250 milliliter aqueous solution contains 45.1 microgram of pesticide. Express the pesticide's concentration in weight to volume percent in ppm and in ppb. So again, remember the weight per volume percent is gram of solid per milliliter of solution times 100. The ppm, remember, is milligram per liter or microgram per milliliter. The ppb, parts per billion, is microgram per liter or nanogram per milliliter. So knowing those, we know the mass of the pesticide, that's 45.1 microgram per 250, that's milliliter solution. And so we convert milligrams to grams, and you come and multiply by 100 to find the percentage. So that's what you have, grams per milliliter. Grams of solute per, this is solute this is solution, grams of solid per milliliter of solution times 100. That's, remember this formula, that's what we have here. And so you got 1.8010 to negative fifth percent, that's weight per volume. To find it in parts per million, again, parts per million is milligram of solid per liter of solution. So you can just, or it is microgram per milliliter. So you don't have to do anything, just divide those two numbers. You come up with ppm, because microgram per milliliter is also parts per million. So for parts per billion, however, it has to be microgram of solid per liter or nanogram of milliliter, a nanogram of solid per milliliter of solution. So here what we do is we just convert the milliliter to liters. So make sure in denominator, so we don't touch this side, it is microgram, but if you just convert milliliter to liters, so make sure in denominator you got liter, then do the math, your answer will be microgram per liter, microgram of the pesticide per liter of solution. So that's 1.8 10 to second, so it's 180 parts per billion. Well, that's it. It's a kind of lengthy video, but it covers a lot of material here, a lot of solutions, making solutions, different types of solutions. So next time we will work on hopefully different topics of analytical chemistry.